Okay, this is a demo of tutorial 2 for our research project. I'll start out with my design and then show the test bench I made. So to use the SIMD function on the DSP slice, I made this module that basically just wraps around the DSP primitive. I know in the Teams tutorial, Wade showed the add sub macro for this. The reason that I didn't do that is because there may be a way to do this. I'm not sure. I couldn't find a way to get the add sub macro to use the pattern detect functionality because it seems like it's hard coded to just do the addition and subtraction functionality. It's an IP, so it's not shown to us, but I'm assuming that the add sub macro is just a primitive like this. That has already had some of these parameters piped into it. Um, I won't go over this part in a ton of detail because I think it's mostly self-explanatory having read the manual for the DSP. I guess for the mask, this is set to ignore the guard lane bits. Since we're only passing in unit 8s, we don't want to pay attention to the uppermost 4 bits when we're trying to detect a pattern. This is how I deal with the fact that the A and B inputs get concatenated into the X mux. So I basically just pipe in the entire operand and then take bits out of that. That's the whole reason that I did this module. I haven't connected it up with the microblaze yet because that's tutorial 3. But my main motive for doing this was so that I could just put 32-bit operands in and out of it and then do the computation in here instead of doing what Wade was showing in the video where we had to do a bunch of slicing and concatenation. This does all of that for me. So I just found it to be a simpler approach and I think it should function the same. I selected this op mode because initially I was doing one that used the X and Y multiplexers, but I realized that that only supports addition. There's no subtraction operation. So I had to change around to this one, which allows me to add or subtract based on a parameter. Yeah, the mode, which is, it corresponds to the ALU mode. So yeah, that's passed directly into the DSP. So is the op mode parameter up there. I have the carry-in as 0 because at least in my test case, I never used the previous result of a computation, and we're not chaining multiple DSPs together. Additionally, for that reason, all of the cascade-related inputs are either bound to 0 or nothing. I have my pattern just set to detect a series of A's. Then I use the uppermost bits of each operation to compute either the carry or borrow. And then for my test bench, it's a very simple monolithic test bench. I was going to do something more complex using a driver, monitor, and scoreboard, but from what I could find, Verilog doesn't actually support that kind of functionality. At least I know for a fact it doesn't support mailboxes, and that's the only way I've implemented that stuff in the past without using UVM, so it seemed like a monolithic approach like this would be kind of sufficient for a pretty simple design anyway. There's not too much to say here. I kind of just pipe the inputs into my DSP instance and then measure the output for a couple different test cases. So I have an addition that shouldn't produce any carries, an addition that does intentionally produce carries on some of the lanes, and then the same thing with subtraction. One of them has no borrows and one of them has a borrow. And then finally, there's one addition that should result in the pattern detect being set because the result is a bunch of A's. And you can see in Vivado that that is the case for all of them. So the one with no carries has no carries. The one that should have carries does. This one has no carries. And then this one, all of the lanes where we borrowed, we, has a borrow bit, and all the lanes where we didn't borrow, it's a 0. And then the pattern detect is 1 for here. I can show my simulation results as well. So there's a period here where nothing is happening. That is because of the global set reset. This guy, was causing a huge bug with my code where, for some reason, all of my inputs were correct until 100 nanoseconds. And I figured out it's because this thing takes 100 nanoseconds to go low, and then your program can actually work. So that took me a minute to work through, but I figured it out. I went ahead and ran the implementation just to show how that's actually being implemented on the board. So you can see I have the one DSP that I'm targeting, and it's just one DSP. Additionally, we have a couple buffers that are used. That's just to store the input and output. And then there are 4 LUTs here. That I'm not necessarily 100% sure if it's okay for me to use. I'm assuming it's probably fine. The reason that there are LUTs to compute the carryout is because it's ORing the top 4 bits in each lane, which is where the carry or borrow bits would be. So I'm assuming those OR gates are probably fine for my overall design. If that needs to change, I am happy to modify it though. But mainly I just wanted to show that it's actually using this DSP slice and only one of the DSP slices on board. I can scroll through these really quick to just show that it's just a couple buffers and that DSP.